Alright folks, this is the main video for this section on conservation of angular momentum. This is our third and final conservation law for AP Physics 1. We did mechanical energy and then linear momentum and now angular momentum. They're all similar. In the absence of a net external torque, the angular momentum of a system remains constant. Now, you would maybe want to go look at conservation of linear momentum and be reminded that that conservation law is due to Newton's third law, that when objects interact, they have to exert equal and opposite torques on one another. They have to exert equal and opposite forces on one another, and therefore the total momentum of the system wouldn't change, even though the individual momentum of each object would change. We're going to skip to the kind of main event and say, now that we know how a conservation of momentum law works, let's look at some situations. But you will also have to answer plenty of questions about a system of objects and whether their angular momentum will change based on what the identity of the system is. So more on that in class. There are three common situations, and kind of within that, a couple extra variations, where you would see conservation of angular momentum. I like to start with the one that is the least familiar, and it's the one that doesn't appear in linear momentum, because angular momentum can change for an object without any collision with another object. So objects that in specific situations can actually change their rotational inertia. So in equation form, we would write the initial angular momentum of that one object is equal to the final angular momentum of that same object. And the math of this situation is fairly simple, because iota and omega have an inverse relationship. If an object is able to increase its rotational inertia, its angular velocity will decrease, and vice versa. The only time the math becomes more difficult is in situations where you might have to calculate the rotational inertia or derive it somehow. Anyway, the simplest example of changing rotational inertia would be orbits, and more on this in section 6.3. But if I were to show an elliptical orbit of a satellite, and show that satellite at two different points along its orbit. So point A and point B. Now, this object we're going to imagine is rotating in the clockwise direction, and it does that all the way around. Now, from point A to point B, the planet or the satellite gets further and further away from its sun or its planet, whatever. We'll say it's a sun and a planet. So the planet gets further and further away from the planet along this path, and then along the path back, it gets closer and closer. Well, rotational inertia for this planet is just going to be m times r squared. The mass of the planet is constant, but that value of r gets bigger and bigger as it goes from point A to point B. So as the rotational inertia goes up, the angular momentum, the angular velocity goes down. The object is using an internal torque to change its orientation, or gravity is performing a torque on it, but that's an internal force. Another example would be, and I'm going to draw a really silly picture, and you might not be able to tell whether, when you look back in your notes, is this like supposed to be a person or is it supposed to be like a machine? It's supposed to be a satellite. And so some satellites, many satellites get their energy from solar panels. And those solar panels don't need to be out all the time. So let's say we have a satellite that is rotating in space and it has solar panels that it can extend. Well, once it extends those solar panels, the orientation of the mass in that satellite changes. And so this initial orientation would be a low rotational inertia, assuming that the axis of rotation for the satellite was down the middle. And then this orientation would be a high rotational inertia. And so what we can conclude is when the rotational inertia of that satellite is low, its angular velocity is high, and then vice versa. When it extends its solar panels and it gains a higher rotational inertia, its angular velocity is going to decrease. So easy math, unfamiliar concept in physics, but one that you've probably thought of maybe when you've watched figure skating or gymnastics. Anyway, now the more familiar ones. You can have collisions that are conservation of momentum situations. Those collisions can be between extended objects or particles, and within that you can have elastic and inelastic collisions. So collisions between extended objects is something that for most of us it's just going to happen in physics class. It's hard to see a lot of these examples in play when you have two rotating objects that are going to collide. But we would write a very familiar expression for conservation of momentum. So if those extended objects were to bounce off one another, then we would write an equation like this. And so this mimics the conservation of linear momentum equation. If the objects bounce, they might bounce elastically or not, but they remain separate all the time. Versus if they happen to collide and stick together, we could modify that equation like this. We could add their rotational inertias. So, I'll do a demonstration where I drop a stapler onto a disc, and both of them will rotate in the end. The stapler and the disc have their own rotational inertia, and they kind of stick to one another when they collide. And so this would be how we would model that collision. So this is if they stick together. So I'll try and do a couple demonstrations of that type of thing there. That's one common situation. But again, behind this is a nice concept. If two rotating objects collide, one of them will experience an increase in angular velocity, and the other one will experience a decrease in angular velocity. And it will be up to you to determine maybe which one that is, and also to remember that the total angular momentum will be constant. The last one can probably be the most varied, and it's also the one that tends to pop up on problems where you need to derive something. Collisions between an extended object and a particle. If you go back to the last video, I showed that at the very end, a ball hitting a beam or something, where they both had angular momentum. So we could write, for example, an equation like this. And the thing that I usually think of is bat and ball sports, baseball and softball, also tennis, field hockey, to a different extent lacrosse. But you have an object that can move in mostly straight lines, and then an object that rotates. Hockey is another one, and they'll collide a lot. And so these two terms would represent the object that can move in a straight line and the object that can rotate, and they will collide in some way. So if they bounce, then we would have an equation like this. And one of the things that's difficult with this equation is remembering which variables are changing, right? So R and M tend to not change, I tends to not change, but those velocities will definitely change. And then the example of let's say lacrosse, if you are catching the ball in your stick, the ball would be coming at your stick with an angular momentum of a particle. Your stick would have its own angular momentum. Now, if you're trying to catch the ball, you're probably not going to be moving the stick around a lot when the ball gets there, so that might be 0. But when they collide, they will have a combined rotational inertia. Oh my gosh, I got that wrong. Sorry. Let me try that again. I was trying to do two things at once in my head. They will have a combined rotational inertia. So that's worth talking about, that this R times M times V is the rotational inertia of a particle. Once that particle becomes part of the rotating system, you can still keep it as r times m times v, but it might be easier to assign it its own rotational inertia and combine it with the other object's rotational inertia. We will do stuff like this in class. This probably looks overwhelming, these like 4 equations at the end, but it's a very familiar thought process of like what has momentum before and after, and are they together or are they separate? And it's just a little trickier to deal with manipulating the variables in the right way. That's it.